Good day, everyone. Our topic for today's video is about the Sieve of Eratosthenes. So let's have first define a prime integer. So it is greater than 1 that is only divisible by 1 and itself. In other words, a prime number has two factors, 1 and itself. Just like for example, we have 2, number 2. So number 2 has factors 1 and 2, right? So the factors are only 1 and itself. Another one, we have 3. Also, the factors of 3 are only 1 and itself. We also have 5, where the factors are 1 and 5. So with 7. And many more. Okay? Now, what about number 1? Is number 1 a prime number? Okay, notice that from our definition of a prime number, it is a number or it is an integer that has two factors for prime number. So it has two factors, 1 and itself. Now notice that 1 has only one factor, which is itself only. Follow? Hence, we can say that 1 is not a prime number. Okay? Now let's have here a term wherein if a number or any integer greater than 1 that is not prime, we call it as a composite number. In other words, a composite number has factors other than 1 and itself. That is, it has 3 or more factors. For example, we have here 4. We know that 4 is not a prime number. Hence, it is a composite number, where the factors of 4 or the divisors of 4 are 1, 2, and 4. So notice that the divisors or the factors of 4 are more than or greater than 2. So it has factors other than 1 and itself. So it has another factor 2. Follow? So it has here 3 factors. Hence, this is not a prime number. Another one is 6. So because 6 has 1, 2, 3, and 6. So these are the factors or divisors of 6. Hence, obviously, this is not a prime number. Hence, this is a composite number. So let's have here a lemma. It states that every integer greater than 1 has a prime divisor. So for greater than 1, we could have 2, 3, 4, 5, and so on. So each number then has a prime divisor. It's a prime divisor or a prime factor. Say for example, we have number 2. So we know that the factors of 2 are 1 and 2. So take note, 2 is a prime number. Hence, this number 2 here has a prime divisor. Now let's have, say, number 9. Okay. So for number 9, we know that the factors of number 9 or divisors of 9 are 1, 3, and 9. So again, we have here 3 as our prime factor or divisor. So for 12, the factors of 12 are 1, 2, 3, 4, 6, and 12, right? So here, there are prime factors. There are two, actually, prime divisors of 12. We have here 2 and 3. So as you noticed here, number 12 has 2 prime divisors. Now take note from our lemma here. It states that it has a prime divisor. There is an existence of a prime divisor. So for the existence, it could be 1, 2, or more. So as long as there exists a prime divisor. So here we have 2 and 3. So let's have here the next theorem. It states that if n is a composite integer, then n has a prime factor not exceeding square root of n. Now take note in this theorem, it can be applied only for a composite integer. So if n is a composite integer, and then we can say that n has a prime factor not exceeding square root of n. So let's try to have our previous example. For a composite, we have 9. Try this, 9. So again, we will write the factors of 9. We have 1, 3, and 9. So we know that the square root of 9 is 3. So not exceeding 3. It has prime factor. So 9 has a prime factor. Of course, we have here 3. 3 is a prime factor of 9. And as you can see, it does not exceed square root of 9. So it does not exceed. What do you mean by not exceeding? It means it will not be more than 3. So more than 3, numbers more than 3 is 3.01, 3.1, 3.2, and so on. So if it is exactly 3, it holds to this theorem. It does not exceed. Now let's have another example. We have 12. So we know that the factors of 12 are 1, 2, 3, 4, 6, and 12. That's it. Now, for the square root of 12, so you can use your calculator or, by the way, I have a video about finding a square root of any number without using a calculator. It is a trick and it is very easy. And sure, you're having fun doing it. Now try to watch it and you will be amazed. Actually, the answer there is just an approximate value. Say we have here square root of 12. So for the square root of 12, this can be written as, you will try to look at the closest perfect square to 12. So the closest perfect square to 12 is 9. So I explained there, actually step by step on how you will do this. So 9 plus 3, it will make us 12. Then after that one, you're going to get the square root of 9. We know that it is 3 plus, you copy this one over, over twice of this. So we have 6. So actually this is 3 plus, this is 1/2. So we can approximate the square root. So approximate, so we have this, the square root of 12 as 3.5. Because the square root of 12 is 3.46 something. So you can round it off to 3.5. Okay. So here, notice here that the prime factors of 12, we do have 2 and 3. So as you can see, the square root of 12 here is approximately 3.5. So 2 and 3 do not exceed, right? Square root of 12. So as you can see, 2 and 3 do not exceed square root of 12. So it holds in our theorem. Because 12 is a composite number, then it has a prime factor. Here, there are 2 prime factors that satisfy the theorem. Okay? So that's it. So let's have here the Sieve of Eratosthenes. So it is an ancient method of finding prime numbers up to a specified integer. So this method was invented by the ancient Greek mathematician Eratosthenes. So here is the algorithm of the Sieve of Eratosthenes. So first, we are going to write a list of numbers from 2 to the largest number n you want to test. Note that every composite integer less than n must have a prime factor less than square root of n. Hence, you need to strike off the multiples of the primes that are less than square root of n. So here, we note here that we use the previous theorem, that every composite integer less than n must have a prime factor less than square root of n. Hence, we're going to consider only primes that are less than square root of n. So we will not be testing anymore those numbers greater than square root of n. Okay, anyway, the answer will be just the same. So to save time. So that's how important this algorithm. So let's try this. Numbers here from 2 to 50. Our n here is 50. So n is 50. So let's try to find the square root of 50. So for the square root of 50, again, let's try to use the trick. So square root of 50, we have the perfect square closest to 50 is 49, and then plus 1 is 50. So this is equal to square root of 49 is 7, plus you copy this one, then twice of this, we have 14. And this is, by the way, this is approximately equal to 7 point. Actually, this value 1 over 14 is 0.07. Hence, we have the square root of 50 is approximately 7.07. So in that case, we will be considering the primes 2, 3, 5, and 7. So less than 7.07. So we have all of these prime numbers less than 7.07. So we will not be testing anymore more than 7. Follow? Because we can get all the primes from 2 to 50 if we only consider rather 2, 3, 5, and 7. Okay, so for the next step, we have strike off all multiples of 2 greater than 2 from the list. The remaining number in the list is a prime number. So we are going to strike off all multiples of 2. So, but then we will not strike off 2, okay? So we will just encircle 2. So we will encircle 2 here, okay? And then we will strike off all multiples of 2 from the list here. So from the numbers here on the table. So we have here, we cross off or we cross out. So multiples of 2, we have 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48, and 50. So we have crossed out all the multiples of 2. So the first remaining number in the list, which is 3, is a prime number. So we encircle this 3. So for our fourth step, we repeat the above steps until no more multiples are found of the prime integers that are less than square root of n. So here, we will be crossing off or crossing out the multiples of 3. So for multiples of 3, we have 6. So it has crossed out already. 9. We have here 9. Next, 12, 15, 18. We have 21, 20, 24, 20, 27, 30, 33, 36. We have 39, 42, 45, and 48. So those are multiples of 3. So let's have for number 5. Here for number 5, we encircle number 5 here and then cross out all the multiples of 5. So we have 10 already crossed out, 15, 20. We have here 25, 30, 35, 40, 45, 50. Okay. So, and the last we have here 7. So we circle number 7 and then crossed out all the multiples of 7. So multiples of 7, we have 14. Other than itself, so we have 14. Next, 21. Okay, already crossed out. Next is 28. Next is 35. Next is 42. And the last, we have 49. So here, we have the numbers that are not crossed out. So after this one, after 7, we will be encircling all the numbers that have not yet been crossed out. So next to 7, we have here 11. Next to 11, we have 13. We have 17, 19, 23, 29, 31, 37, 41, 43, and 47. So here, the encircled numbers here in our table are all prime numbers between 2 and 50. So notice here, there are how many prime numbers? We have 2, 4, 6, 8, 10, 12, 14, 15 prime numbers between 2 and 50 or from 2 to 50. So that's it. So that's all about finding prime numbers using algorithm of the Sieve of Eratosthenes. Thank you for watching and listening. God bless everyone.